So I will skip the slides on the ISCA, describing ISCA, and go to the examples that we have from Annexure 6, which is Power T&D. We have a so-called case book. Where is it now? Here. Where you can find on the web a number of cases, not only from Europe, but also from other places. And I will give some examples of cases that we have studied. One is the so-called East-West interconnector between Ireland and England. And as you might know, Ireland has a very, very high penetration of wind power. And today, or historically, they had to curtail quite a lot of wind power. And by building an interconnector with England, they could balance the wind on Ireland. But they also had other benefits because they actually choose to have a voltage source DC converter. And the reason by having that is that they can have multiple services that are beyond what you normally find in a transmission grid. Like you have reactive power control, you have voltage control, frequency control. They have even a black start function on this link, which hopefully they will not need. But it's an example of what you can do with modern transmission. One thing that is very interesting with this project is that it's a beautiful example of community involvement. They had a very good dialogue with stakeholders, including that they had were inviting classes to become interested in study engineering, which is, I think, a very good way to use a good technology project. So the result with this is, to make it in short, it has proved that it does the job from an electrical point of view, but also from a market point of view. It has reduced the prices considerably on Ireland, which was one of the purposes. Then another project deals with photovoltaic and integration of photovoltaic. And if you're engineers, you should read this example because it's a good example how you can use advanced controls to enhance actually the capability of photovoltaic. And the goal they wanted to show that by having advanced controller on the PV, they could reduce the demands on the distribution grids. And what they have studied here is, as you can see on the left here, they have studied a large number of different control strategies. And they have showed how they perform then from different perspectives. And for those of you that are considering photovoltaic, I think read the report and you will find a lot of good examples on how different control strategies work out. One of the results is that they have actually been able to prove that you can, by having advanced controllers, you can reduce the requirements on the distribution grid. And they have also shown, which is interesting, that by having distributed controllers, you have a more efficient control system than if you have a centralized. So those of you that believe in distributed control strategies should read that. You get a lot of support for your ideas in this report. So overall, the goal was to show that they could increase the capacity of the grid by 50% at an investment cost that was 10% only of traditional grid investments. And the proof is in this report. Then Denmark is one example which is interesting because there they have actually integrated, I will go to this slide only, they have integrated a heat system with the electricity system. When we talk about smart grids, we shouldn't forget that the power we send in the grid is used to something, and if the final use is to produce heat, then you can use heat storage rather than electricity storage. And this report shows how this is done. Another example which shows that things doesn't work out always as you plan is in Italy. Actually, they have used a quite big scale test of time of use tariffs for electricity customers. And the result is that the time of use tariff is not enough to change customer behavior. So even an example that shows that it didn't work is interesting because don't be too optimistic about time of use tariffs. You need something more probably to make a difference. Then last example is from Sweden. It's an interesting project. What is interesting with this project is that there was a need to reinforce the grid in Sweden from north to south. And the project is a combination of different technologies, AC technologies, DC technologies, DC overhead and DC underground. And maybe the most important part of the project is the last 200 kilometers is actually a fully underground transmission line. I believe it's today the biggest underground transmission line. You can also find that the reason underground was chosen was that to save time, actually. And the reason voltage source DC converter was used, they needed also the controllability of the link to stabilize the grid. You will find in Europe, in fact, that increasingly now you will see underground transmission lines. For instance, the new reinforcements in Germany planned will be partly underground and maybe even mainly underground. So the lessons learned is if you build transmission, build a smart transmission system that also can control voltage and reactive power control. And that will even increase the capacity on the existing AC grid. So that was my minutes. Thank you.